Hi, I'm Martyn Heyne and I run a music studio in Berlin, Germany. In the context of that, I find myself answering recurring questions and discussing certain production techniques on a regular basis. That's why I've decided to start this short video series to address some of those subjects for my clients as well as anyone else who might benefit from it. In the last episode, we spoke about pressure transducers or Omni mics, and today let's try and better understand the other type of microphone that you'll find absolutely everywhere. It's called the pressure gradient microphone. This would be anything with a cardioid, wide cardioid, super cardioid, figure of 8 or anything like that pickup pattern. In other words, any microphone that is directional. As we will see, this directionality comes at a high price. And after raving about the qualities of the pressure transducer at some length in my other video, I wanted to answer the question as to why this directionality is so valuable right away. After all, didn't I say our ears were pressure transducers as well? And they can pick up everything, right? Yes, but crucially, after we get the signal from our ears, we run it through the software of our minds. So while our ears hear everything, our mind only listens to a selection of that. Our ears hear the entire bar, but our mind only listens to the person that we're having a conversation with. Now, in order to paint the sonic landscapes that we wish, it takes a microphone that has a similar selectivity. Disclaimer. As you can tell, this video is going to be something of a continuation of the video about Omni mics. So if you haven't actually watched that one yet, I recommend you do that first. Okay, so let's have a look into how pressure gradient microphones are actually constructed. We have our membrane again, but this time it's not covering a pot. Instead, it's suspended freely and accessible from both sides. Imagine a super thin sheet of material tensioned over a supporting ring. This is the membrane and this is the suspension. Now, a sound that's coming from over here would reach the front of the membrane earlier than one that would have to go round the back first. This delay between the two sides causes a phase shift. So here you have the earlier waveform and here the delayed one. So now you have a different moment of the waveform in the front of the microphone than in the back. This is the membrane. This difference between the 2 points is the pressure gradient. This is what moves the membrane and what the microphone picks up on. Alright, so here's the same membrane again, but this time let's say the sound arrives from a 90-degree angle, exactly from the side of the microphone, from here. We can see in that case the sound takes the exact same time to get to the front and the back of the membrane, so there is no delay and no difference and therefore no output. So we get maximum pickup from the front and then gradually less until there is, at least in theory, nothing from the side anymore. Voila, directionality. This is the most basic form of the pressure gradient microphone, and as you may have recognized, it creates the figure of 8 pickup pattern. This is because if we move on to the back of the membrane, the difference will increase again until from 180 degrees is just as sensitive as it is from the front. Except the signal is now in opposite relative polarity as it moves the membrane in the opposite direction. Membrane in the middle again. Now, in order to get from this to the cardioid pickup pattern that we all love so much, we can start to obstruct one side of the figure of 8 with all sorts of partially permeable constructions such as little sound tunnels or friction resistors or resonators and passive membranes, etc. To simplify, consider that if you obstruct the microphone from the back, it will become less sensitive from there, but at the same time it will begin to be sensitive from the side because the front and the back of the membrane are no longer the same, and therefore a sound that is arriving exactly from the side at a 90-degree angle will no longer cancel out. The constructive aspects of a pressure gradient microphone are really fairly complex. That is because the frequency response requires a lot of equalization, which is more often than not done acoustically through the design of the microphone. As a quick example, consider that the pressure gradient varies with frequency. So here we have a low frequency, and here we have a higher one. This is the front of the membrane, and this is the back of the membrane, and the space between them is the time delay. So now you can see that the gradient, the difference between the front and the back, is greater for the higher frequency than it is for the lower frequency, even though the amplitudes of the two frequencies are about as similar as my absolutely abysmal drawing skills were capable of conveying. This effect is regardless of the distance to the source and basically tilts the entire frequency response and needs to be addressed in the microphone's design. So in conclusion, there is a necessity to implement constructive measures in order to flatten and extend the frequency response of a microphone through resonance chambers or even a high frequency cone in front of the membrane and so forth. In some modern microphones, such as the Sennheiser MKH range for example, these equalizations are done electronically rather than acoustically. But for now, let's not get any deeper into this, because whatever the manufacturer did to create the tonal response of their microphone is then what it is, and does not really show any variation depending on use. But another tonal aspect really does change considerably depending on application, so let's look at that. I'm talking, of course, about proximity effect. All pressure gradient or directional microphones create an overemphasis of the low end when addressed at close range. This is called proximity effect. The exact cause for this is curiously not fully understood, and there are a few varying explanations out there. But in any case, we know from experience that the effect is connected to the near field of the microphone. So let's take a look at what happens there. Low frequency sound propagates in space as a spherical pressure wave. It's not a ray or a two-dimensional wave, but an expanding sphere. As a result, the curvature of the wave straightens out relative to an object of the same size at different distances. Now let's say this dot here is the sound source, and these two lines here are microphones at different distances. Now you can see that the sound wave appears more curved to the microphone that's in the near field than it does to the one that's further away, where the wave is almost straight. This area is called the near field, and its size is frequency dependent. Let's zoom in on our membrane again. Here we see the membrane of the microphone again, and the suspension, and then a straight wave and a curved wave. You can see that for the curved wave, the time it takes to travel round to the other side of the membrane is even longer than for the straight wave. So this means the difference between the front and the back is greater, and the corresponding signal will be louder. In effect, this means that the overemphasis will increase as you get closer to the source. From experience, we can say that proximity effect ceases to appear for a given frequency if the distance to the source is one wavelength of that frequency or more. We can also say that the figure of 8 pickup pattern creates the strongest proximity effect, and as the pickup pattern gradually moves via cardioid towards omni, it progressively softens. However, in practice, we cannot look at proximity effect as a physical phenomenon alone and, for example, say you should always keep a singer 50 centimeters from a cardioid microphone or something like that. In real life, all microphones are different, and their tonal response depends on their structural design, as mentioned earlier. So the situation with proximity effect will also vary from model to model. What you can rely on, however, is the tendency that proximity effect will grow stronger or fainter depending on whether you increase or decrease the distance to the source. As an additional tip, with a cardioid microphone you can also vary the address angle a little bit in order to soften proximity effect. So instead of addressing the microphone straight on, you could tilt it a little bit. Some manufacturers also implement some sort of switchable roll-off filter for the low end, like on this 421 here. It's got 5 settings to accommodate varying distances, and you can set it from M for music, which means no roll-off, gradually to S for speech, which means the strongest roll-off. Here a word of warning about directional mics in general. The manufacturer will usually publish a frequency response graph of the microphone on axis. But as you move down the side, for example on a cardioid microphone, the sound will not only get softer, as the cardioid pattern would suggest, but usually also have some shift in the tonal response as well. This is significant. You want your directional microphones to have a great off-axis sound as well as on-axis, as those off-axis sounds will be your ambience and the bleed from other instruments, and depending on your style of recording, they may make up a sizable part of your overall sound. Now, before we get too upset about proximity effect, let's look at all the ways in which it can actually be beneficial. The classic speaker or crooner voice that is so warm and full and close would not actually be possible without the coloring properties of pressure gradient microphones and proximity effect. Also, if you wish to make your little combo amp sound more like a 4x12, proximity effect will help. And dub producers have long since discovered that if you stick a microphone in the back of a bass cabinet to get closer to the speaker, you can achieve a fuller sound. Another plus of the pressure gradient microphone is that they exhibit none of the pressure buildup that we discussed when looking at omnis. However, they are unfortunately much more sensitive to handling noises, rumble and wind than their pressure transducer counterparts. So again, there's no one-size-fits-all with microphones, but rather you have to decide what your priorities are and then make informed choices accordingly. I hope this video was of some help for doing just that. Thanks very much for watching. If you have any additional questions or your own experiences to share, please do so in the comments. Also feel free to forward this video to all your recording friends, and make sure that you subscribe here to be notified about future episodes. Thanks very much. Goodbye.